Right, so this is just a quick review on what we learned on maximum shear stress. Most important thing you have to know, like what I keep on emphasizing down here, you have to know what loading it is, okay? Whether your 3D mold circle look like this or your 3D mold circle look like this, okay? So that's why constructing 3D mold circle is important. Now, the next thing that we're going to go for is what we call vortices. Okay, vortices criteria. So vortices criteria, it is based on distortion energy. Okay, it's based on distortion, and it is per unit volume. Right? So it focus on the distortion. Okay, so focus on the distortion that occurs in the elastic region only. So you cannot use vortices criteria for plastic stress. Okay, when you are in the plastic region, it only focus on the elastic region. So now if we have a 3D element again, so this is our X, Y, and Z, and we have our element. So our element, we have stress X, we have stress Y, and we have stress Z, okay? And the distortion energy, I'm not going to derive the distortion energy equation out, but I'm just going to tell you the form of the distortion energy. Okay, so the distortion energy, which is UD, capital U and small d, is equal to 1 over 6G, okay, bracket squares A squared minus stress A, stress B, okay, plus by stress B squared. Okay. And stress A and stress B are the principal stresses okay, in 3D mold circle. Okay. And G over here is the modulus of rigidity. And you have seen this before. In what sense? So if you have shear stress is equal to G of gamma, okay, where gamma is the shear strain. Okay. So its equivalent is the normal stress is equal to Young's modulus multiplied by strain. Okay, where epsilon is the normal strain. And you do get, I think if you were to look at the materials handbook, okay, you do see the value of G. Okay, let me get the textbook out. Okay, so now I believe you can see the textbook. And if we go far down enough, right, where is it? Yeah, So if you look at, I'm going to copy the table. And I'm going to paste over here. Right? You can see this line over here, right? This is the modulus of rigidity, which is G. Okay, so it is used to calculate the relationship of shear strain to shear stress. Okay, it's like equivalent to our Young's modulus. Okay, right. So that value is from Materials Handbook, as where you can you saw where I get it from. Now the maximum distortion criteria carried out by von Mises, okay, is based on experiment. Okay, what do I mean? What do I mean by that? Okay, what do I mean is based on experiment. So what he did, okay, hey, how come I cannot go to the next page? Oh, let me go page 3. So what he did, what von Mises did, okay, von Mises criteria, criteria is based on the experiment that was carried out. So he did something different. So what he did is he carried out uniaxial tensile test. He carried out uniaxial tensile test. And this is, if I were to draw our transformation, this is our X, this is our Y, and this is our Z. He did a uniaxial tensile test. Okay. So from here, he analyzed an element. All right. So when he took out the element is basically in this form. Okay. And we know the element is under stress X. With that, he called this surface X. This surface over here, he called it Z. And this space over here, he called it Y. Okay. So when he constructed, or when we construct a 3D mold circle based on this, is pretty straightforward. You can already anticipate how it looked like. So we have normal stress. Then we have our shearing stress. Okay. And we are aware that over here, this is our normal stress X, normal stress Y, and normal stress Z. And over here, this is our point X, and the other point is our point Y and our point Z. Then again, we construct 3D mold circle. And again, because X and Y are in a single point, this is how our 3D mold circle will look like. Right? So we call this point over here, okay, this is our stress A. And we call this point over here, this is our stress B. Okay. So based on, so from here, based on uniaxial experimental test, right? We will get the structure will yield when stress A is equal to stress U. And for this case, we know that stress B is equal to 0. Okay, and stress Y is our, or stress capital Y is our U strength. And as I mentioned to you before, U strength is from experimental work. We cannot calculate our U strength, we have to do experimental work. Okay, there are research going on that I'm doing to calculate U strength, okay, by prediction. Okay, so this is usually done by by experimental work. So we are going to write this UD, and this is Y. Okay, Y, whenever you see Y over here, this is our U what? Or this is at U. Okay, Y means this is experiment. Okay, so this is equal to 1 over 6G bracket stress A squared minus by stress A stress B minus by stress B squared. Okay, so as you can see over here, right? So let me define capital U small d bracket Y. This is the energy required to induce UD. And this happened, so by looking at this expression over here, and by putting in what we know from the 3D mole circle, right? So from 3D mole circle, we know that stress B is equal to 0, stress A is equal to stress U. Okay, so when this is the case, UD at U is equal to 1 over 6G, okay, bracket stress U squared. And that's it, because the rest are equal to 0. Sorry, this last term is a plus. Okay. So they are all equal to 0. I should not put bracket 0 because there's no. So this will be equal to stress U squared divided by 6G. And this is our distortion energy due to yield from experiment. Okay. Now, based on structure, so how do we use this condition down here? Okay. How do we use this condition down here? Okay. So it is based on, so let's say we look at the equation based on structure analysis, right? The structure is safe, right? When UD is less than or less than UD at U. Okay. So over here on the left hand side, okay, this is U, yeah, not V, sorry. U E. Okay. It looks like a cursive V when I write it that way. Okay. So on the left hand side, it is due to or determined from structure analysis. On the other side, the expression is due to mechanical testing under uni-axial loading. Okay. And again, we are using principal stresses. I repeat again, we are